So, today we will be talking of rotational motion of rigid bodies. In rotational motion, some of the words come very frequently and very important to analyze any such situation, and some of these are angular velocity, which we write as omega. Then we have angular momentum, which we write as L. We have moment of inertia, which we write as I. We have torque, which we write as tau. You know all meanings of all these things, I believe so. So, angular velocity is a vector quantity omega, and if you have a rigid body which is rotating, and if you find that velocity of any particle, linear velocity of any particle can be written as omega cross Ri. Ri is the position vector of the particle, and this omega is same for all the particles, then you say that this rigid body has this angular velocity vector. So, that is how one can identify omega, and if something is rotating about a fixed axis of rotation, or at any instant if you can find axis of rotation, then it is very simple. You just write the magnitude of angular velocity omega as d theta dt, and the direction is along the axis. If things are rotating anti-clockwise, it is towards the viewer; if it is clockwise, opposite to the viewers. So, that is angular velocity omega. Then you also have angular acceleration. With this you can also define angular acceleration alpha, which is d omega dt. So, this is angular acceleration then angular momentum L. For a particle, it is Ri cross Pi, which is Ri cross MiVi, and summation over all the particles. So, that is the angular momentum of the thing, and then you have torque. Torque is also a vector quantity. Torque is R cross F. So, Ri cross Fi. So, look at all the forces, and we are talking of external forces only. So, look for all the forces, and if that force acts on ith particle, then do this cross product Ri cross Fi, and then sum over all those i's. So, essentially this I runs over the forces which are acting on the object, the external forces. So, at whatever point these forces are acting, the position vector of those points. So, these are the things. Moment of inertia is something which is more tricky, and probably I will not be talking about this much. Now, some of the elementary textbooks define moment of inertia about an axis. They assume that this rotation is about a fixed axis of rotation, and then the definition of this I is simple, and that is summation over mi Ri square. Then you sometimes hear that torque is equal to I alpha. So, equations like that, or L is equal to I omega, equations like that. Okay. But these equations are valid in certain situations only, not everywhere, valid for certain situations. So, these are the terms used when you talk of rotational dynamics. So, first let me talk in terms of a conical pendulum and see what are these quantities for that conical pendulum. So, here is a pendulum, here is a pendulum. If I just move this pendulum like this, it is a simple pendulum, but if I move it in a cone, this thread goes in a cone, it becomes conical pendulum. So, I am rotating it as a conical pendulum. The ball is going in a horizontal circle, the thread is going on the surface of a cone, and you can take some semi-vertical angle theta of this cone. The questions we will be investigating: what is the angular velocity, which direction, what is the angular momentum, what is the torque, what is the angular acceleration, and what are those relations that are there. So, let us do all those things on the board. So, the conical pendulum is like, you can draw a picture, ball here, and then it goes in a horizontal circle, anti-clockwise as seen from above. This is that point where the other end of thread I had held. This is that vertical axis, and the semi-vertical angle is theta. So, first let us see what is angular velocity omega. The magnitude depends on how fast I am moving it. In one rotation, the angle rotated is 2 pi. So, you can take center of the circle, and from here you can connect this ball. So, the ball moves and the angle theta changes. So, it is going like this in this circle. So, you can ask what is d theta dt or delta theta delta t, that is the magnitude of omega. And if I am maintaining this rotation at a constant speed, then at a constant rate, then this omega is constant, and its direction is along this axis of rotation, and in our case it is vertically upward because the ball is going in anti-clockwise direction. So, the direction is this is the direction of this omega, vertically upward. What is angular acceleration? Angular acceleration is d omega dt, but omega is constant in magnitude as well as in direction. The direction is always vertically upward and magnitude is fixed if I am rotating with a constant rate. Therefore, this angular acceleration is 0. Next is torque. So, let us calculate what is the torque on this ball, rotating ball. So, this is a point of suspension and I take my origin here. So, torque on this ball is summation Ri Fi. So, I have to look for all the forces, and for each force I have to find this Ri cross Fi, and that torque I have to add vectorially to get the total torque. So, here the forces are tension of this thread, here is the particle, and then weight. These are the two forces that I can see, and the torque of this tension force about this origin should be 0, because if the force is acting at this point and origin is here, this r vector is from origin to the particle where the force is acting. So, this is r vector, and the force vector is also along this same thread, and therefore, they are parallel and will be 0. So, torque of this tension is 0, torque of mg you have to write. So, this is Ri, once again it is here. So, it is about this, this is r, this is r vector. So, let me write some letters, let me call this point A and let me call this point as B, this center of the circle as B. So, Ri for this point is OA vector and cross mg vector, and this OA you can write as OB and plus BA and cross mg, and then OB is in vertical direction, mg is also in vertical direction. So, this cross product will be 0, and so it will be BA and cross mg vector. What is the magnitude? BA is radius of this circle, this is radius of this circle, mg, the magnitude is mg, and then sin theta, angle between BA and mg. BA is horizontal, mg is vertical, so angle is 90 degrees, and therefore sin theta is sin 90 degrees, which is 1. So, this is the magnitude. And so, you see that the torque is not 0, the angular acceleration is 0, but torque is not 0. So, it is not always true that torque produces angular acceleration, torque is equal to I alpha and all those. If alpha is 0, torque should be 0. It is not always true. So, now I am showing you a very interesting demonstration which will show the relation between torque and angular momentum. This experiment is generally done with cycle wheel. We have done some miniaturization. So, in this I have taken a CD, a used CD, and on that CD I have fixed a motor here and a battery here. Motor, battery, they are all fixed with the CD, and this entire setup is hanging through this thread from some support. So, that is the setup. On the other side you can see a toothpick. This is just to show the axis of this CD, the direction of axis of the CD. So, because of that it is here. The thread is put, if I keep this CD surface vertical, then the thread is not passing through the center of mass. The center of mass is towards the CD side, and therefore, if I leave it from here, it tilts, it does not stay like this, it does not stay with the surface of the CD vertical. If I leave it from here, it tilts. So, this tilting also we can understand using rotational dynamics equations. Suppose it is in this condition and I will be leaving my hand and it will be tilting like that. So, let us analyze that. What are the forces on this setup? One is weight, which is passing through the center of mass, which is vertically downward, and the other is this tension in the thread. So, if I take the center of mass as the origin and write all my torques there, the torque of the weight mg will be 0, because the line of force passes through that center of mass. So, r vector will be 0, r cross f will be 0. So, we have to find the torque due to this tension only about the center of mass. The center of mass will be somewhere here in the middle, because motor is the heaviest part. So, it will be close to the center of the motor, and then this thread is tied here. So, this you can take as the point of application. So, from here the force is acting. So, from this origin to this point, that is vector r, and this is vector f. So, if I draw this picture on board, I can explain better the direction of the torque. So, it is something like this. You have all this system, and the center of mass is somewhere here, and the thread is passing through this point. So, this is the tension T, and here is the origin. So, this is the vector r, this is vector r, here is the origin, center of mass, and then the thread is tied at this point. So, tension is here. So, this. Now, I can write this r in two components. One is this and another is this. So, what I need is r cross f, or r cross this tension, r cross f, and this r has two components. Let me call this point as A and this point is B. We had done it earlier. So, this is OA and plus AB, and cross product with force, which is the tension here, and this AB and cross this tension, that will be 0. So, it is essentially OA cross F. So, what is the direction of OA? This is the direction of OA, and F, this is the direction. So, where is the torque? What is the direction of the torque? So, R cross F, it is going into the board. The torque is going into the board. So, if I look at it here on the system, this vector R, or this OA vector is like this toothpick here, and force vector is here, tension is here. So, R cross F, this R cross F will be towards me. So, torque is towards me, the change in angular momentum should be towards me, because torque is dl dt. Initial angular momentum is 0. So, after time dt, the angular momentum direction should be towards me, and if angular momentum is towards me, it has to tilt anti-clockwise in that perpendicular plane. So, it goes like this, and that is what it happens. When I release, it goes like this. When I release it from here, it just tilts like that. So, that is how things are explained. So, now I will connect this battery to the motor, so that this disc will start rotating. So, let me remove this axis. If needed, we will put it back and connect it here, and you watch whether it goes clockwise or anti-clockwise. So, as seen by me, it is going clockwise, and as seen by the camera, it is going anti-clockwise. So, I am keeping the CD surface vertical and releasing it, and see what happens. See, it is rotating about a vertical axis, but the CD surface is almost vertical. It is not tilting, it is almost vertical. whereas if I do not rotate it and then release, it tilts. So, how come it remained vertical and started going around this vertical axis? So, let us try to understand that. Let me put this axis back here. So, now let us understand why it started rotating and the surface remained vertical. Once again, the situation as far as the torque calculation is concerned, it is same as that shown on the board. When in that whole process, when the CD is here, motor is here, battery is here, then the torque is just like that and the torque direction will be towards me. So, this is the torque direction, and if this is torque direction, the angular momentum change will be produced in this direction. Since it is spinning fast, there is already an angular momentum, large angular momentum in this direction towards this axis, along this axis. So, that L is already there. Then you have a torque towards me. So, that is in which direction? That is in this direction. So, here is the torque direction, and that is also the direction of change in angular momentum in some time dt. So, this is L and this is dl. If dt is small, this dl is also very small. So, when you add this L vector and this dl vector, what is the new angular momentum? The new angular momentum, which is vector sum of this and this, will be between these. Use parallelograms, it will be like this. To get the angular momentum in this direction, the entire CD has to turn, so that this angular momentum is rotated by some angle in this direction, So, from here angular momentum, it has to come in this direction, and therefore, this CD has to rotate. So, to produce the same dl, because the torque remains the same in the same direction. So, to produce the same dl, if this CD is initially stationary, it has to tilt like this, but if it is initially spinning, it has to rotate like this, and that is why when you connect this battery to the motor and spin this CD fast, it goes round this vertical axis and the surface remains almost vertical.